All right, looking at example 3 here for our second video here in section 8.8. Let's say we want to integrate from negative infinity to infinity of cosine of pi x dx. All right, so here I got kind of an idea what's going to happen because I know my cosine curve repeats itself constantly. It's like that wave curve that goes from positive 1 down to negative 1 back up to positive 1, and it does that going in both directions. So cosine of pi over x, it exists as x approaches both negative infinity and infinity. So again, let's break it into two integrals. And a good place to have 0 is right in the middle. Now, this looks like it's going to be a lot of work, but the nice thing is when you integrate this and when you evaluate, the zeros are going to be the same. So, we're just going to copy some of our answers here. So again, we're going to treat this as the limit, as it could be t, it could be b, whatever variable you want to choose is fine by me. So as b, I'm going to put in b this time as b goes to negative infinity, and then as b goes to positive infinity up here. So let's integrate this. So if we integrate cosine of pi x, that's going to be sine of pi x, but then you got to take the derivative of the inside, which is pi, and then divide it into our sine of pi x, or multiply it as 1 over pi. So both of these integrations are the same. We just have to choose our two different boundaries. So if we put in 0, sine of pi times 0 is 0. So if you think of your unit circle at 0, that's the y coordinate, that's a 0. And we put our b in for x, so minus 1 over pi sine of pi b. And so plus, all right, the b, that's the same thing, so 1 over pi sine of pi b. And then minus, you put in the 0, that's 0. So how convenient, these two just switch around. That's why 0 is so nice. Let's take the limit. Okay, as I go to negative infinity, what's happening here? Well, for the sine curve, just like the cosine curve, it's waving up and down between negative 1 and 1. All the pi over b is going to do, it's just going to make it go faster because we're squeezing the curve together. So it's bouncing up and down, up and down, up and down, up and down, up and down. It's not converging to anything. So the limit doesn't exist. So that's technically diverges. And that's going to be the same thing as if you go to positive infinity. So as soon as you get one that diverges, the whole thing diverges. Example 4, okay, here we go from negative infinity to 0 of x times e to the 2x dx. All right, so let's see. E to the 2x, that's an exponential function. That kind of goes flat and turns and goes up. X is a linear function, so that goes up as well. So there's no restrictions in there. So I think we're going to be continuous the whole time. So we are good as we head up to negative infinity. So again, change this up. Put in your t, put in your b, whatever you want for your negative infinity. Treat it as a limit. And we'll integrate this. Oh no, this is an integration by parts, so multiplying two functions together. All right, so let's see, L-I-A, well, exponential is at the end, algebra, so we'll let our u be x. E to the 2x will be our dv. So e to the 2x dx. If I take the derivative of x, that's dx. If I integrate e to the 2x, that's e to the 2x, but then take the derivative of 2, you got to divide that into that. So e to the 2x over 2, or 1/2 e to the 2x. However you want to write it, it's fine by me. So let's plug everything in. So u times v, so 1/2 times x times e to the 2x minus v times du. Well, let's just factor the half out to the front. E to the 2x d. Oh, I already integrated that. That's right here. How convenient. So let's integrate this. Just replace it with 1/2 e to the 2x. So that becomes 1/4 e to the 2x. And if it was a definite integral, or indefinite integral, it would be plus c. But we have our bounds. So I'm just going to copy this right here, and we're going to evaluate it from our lower bound of b up to our 0. So we plug in the 0 first. Oh, that's perfect. 0 goes in for x. That's all 0. 2 times 0 here, well, wait a minute, that's 0. E to the 0 power. Any base to the 0 power is 1. So it looks like we're going to just get 0 minus 1/4 for the 0. For the b, well, we put a b here for the x, we put a b here, and we put a b there. So now we're going to start taking the limit as b goes to negative infinity. Okay, so, well, don't worry about this b. I'm going here to the power. This is e to the 2 times negative infinity. That's a negative exponent. That goes into the denominator. Doesn't matter if I'm going to negative infinity on the top. On the bottom, I'm going e to the 2 infinity. It's getting bigger faster. This approaches 0. Well, here this has to approach 0 too, because that's going to be 4e to the 2b, or excuse me, 2 to the infinity. I can't talk here. E to the 2 times infinity power in the denominator. That 2 is going to 0. So this whole thing is going to equal 1/4. So the limit exists, so it does converge. And that's my area. Wow, negative area. So that means, let me double check. That means we have to be underneath the x-axis. So let's just test this out real quick in our calculator. So here's my x, e to the 2x. And let's see, let me check my window here. So negative, here's something I think we need to do is negative 10 to 10. I changed and got rid of my y min from negative 10 to negative 1, y max to 1, and counted by 0.5, and I graph it. Yep, sure enough, there it is. From 0 out to negative infinity, I'm staying underneath the x-axis. So let's see, since I'm out here at negative 10, right? Check my window again. Yep, negative 10. Graph, second trace. Integrate 7. We're going to go lower bound negative 10 to 0. I'm already there, negative 0.25. I am getting there really fast. I don't have to make this thing go out any further. It's approaching negative 1/4 so fast that we're there by the time we get to negative 10. Does it get even bigger? Well, let's find out. Change your window, make it a negative 100. Graph it. Second trace, number 7. Lower bound, negative 100. Enter upper bound 0. Still negative 0.25. There's hardly any air there to be adding to that negative 1/4. So yep, that's the area under my curve. It's verified. I'm believing now. All right, next example 5. We're going to integrate from negative infinity to infinity of e to the x over 1 plus e to the 2x dx. So again, both curves are going to exist as we go to negative infinity and infinity, but I have to break it in the middle. So again, 0 is always a good value. Whoa, slow down, mouse. So here, we'll begin t or b, whatever you prefer, in for the infinities. So in this problem here, 1's a perfect square. E to the 2x, that we could say is e to the x, all that squared. That's a perfect square. And I think if I were to use a little u substitution, I think I have an inverse tangent answer here. So let's let u equal e to the x, and that way du is e to the x dx. So that will put du up in the numerator, and this will give me 1 plus, yep, u squared, yep, and this becomes my inverse tangent of u. Now, I didn't change my bounds with relationship to u. So I'm just going to integrate it real quick with the u's, and then I'm going to substitute back in my e to the x when I'm ready to evaluate it. Okay? So I've already integrated it. Good. We're ready to put in the 0 and the b, but we should get rid of the u, and let's put e to the x back in. So let's put e to the x in both of those. All right, let's put in our 0. So inverse tangent of e to the 0, that's a 1, minus inverse tangent of e to the b power, plus our limit as b now goes to positive infinity, inverse tangent of e to the b, minus inverse tangent of 1, because they're basically the same. We're just switching around the minus sign. Okay, so let's see. What do we got going here? So my inverse tangent of 1. That sounds familiar to me. That's tangent is opposite over adjacent. And if to get a 1, you both have to be the same. That means it's a 45 degrees or pi over 4. So these two are pi over 4. Oh, wait a minute. Hold the phone. One's going to be a positive, and that's going to be a negative. Oh, great. They just canceled out. I thought we were converging for a second. Okay. Great. What happens? Inverse tangent goes to a 0, and what happens going to infinity? Let's see. I got to think of my trig. I got to think of that graph. I think that's that tangent curve. It kind of looks like a cubic function, but it's got to be on its side. So if you reference the graph of the inverse tangent, you will have a horizontal asymptote at pi over 2 and negative pi over 2. And here's my graph. And so as I approach 0, right, inverse tangent of 0, as I do my limit there, it's 0 right there. And now for the tricky part, now I'm heading to infinity. So the inverse tangent of infinity, well, I'm going to keep going out here, and I'm approaching this horizontal asymptote. Okay, that has to be approaching pi over 2. That's this part right here. So 0 plus pi over 2, we're going to pi over 2 for, I believe, our area. So since the limit exists, it's convergent.